Okie dokie. Right, back to part 6. No, day 6, part 2. I am supposed to be doing holiday planning, but I think a quick 30 minutes on this should be fine. So, where we left yesterday, have successfully built our test map. Now we just need to do part 1, and part 1 is going to count all of the orbits. So, around COM, B orbits directly, that's 1. Around B, C orbits B directly, that's 1. C also orbits COM indirectly, that's another 1. So in these first two lines, there are 3 orbits. Another 2 for this line, for 5 orbits. Now E orbits D directly, that's 1. It also orbits B indirectly, that's another 1, and COM indirectly, that's another 1, for an extra 3 from this line. So 8 in total. The sample input is the one we'll be testing. This comes to 42. That test is already written. Part 1 on test data. Test joint, day 6. Yeah, should be 42. Now, from one node, we want to count children. It's going to take a reference to self, and it's going to return a use size. This can never be negative. And we're going to start out with the number of children it has. So if we bring that sample text up again. So we reach COM, and we say, well, COM has 1 child, that's B. Then we'll recursively do the same for B. Ooh. We need to make sure that we add 1 on every layer. Because we're eventually going to go down to C. We're going to say C has no children. We're going to go back up to B. Well, let's see what happens. So first off, let mute count 0. If let some children self children, I mean, for child and children, count 1 plus the number of children it has. So let's see. Count 1 for B. B has a child C. You do a count on the number of children. B is the child. So you do a count on the number of children B has, which is 2. But that's going to recurse. So you'll get a 1 when you recurse into this. Well, 1 just before you recurse into this one. You'll get a 1. I think that's probably right. There's some syntax I think could probably help out somewhere here. We've done if let sum, which says that if the value is an option, or in fact a result would be fine here as well. Basically, you can pattern destructure, enum destructure in here in a pattern. So if it's a sum, do this. If you want to do an early exit, you can also do let else, which hopefully I think it would have been helpful somewhere somewhere up here, but we might have a look. We're going to return count. Now, count here is going to reset to 0 for each recursive call. Well, I mean, let's see what happens. Part 1, we are going to do head.countChildren. We're just going to return that. That returns an eye size. Yeah, I mean, there's no reason this needs to be an eye size, but fuck it. This stream is not for children. Cargo test day 6. Let's see what happens. Failed. Okay, cool. What did we get to? We got to 11. Yes, I thought that might happen. Right, let's see. It's possible this needs to go the other way, and we need to count. From COM, we can't recursively go down necessarily, because COM does not know how far down we're going to go. Each time we go down, we have effectively add multiple layers, because we need to add 1 for every parent, grandparent, every ancestor of a child. Now, children don't know who their ancestor is, so for each child, so the problem is this count 1 plus child.children count, because by the time we get to D, well, actually we want the count to be a direct orbit, an indirect orbit. Once we get to E, actually, once we get to E, we want count to be a direct orbit and 2 indirect orbits, which presumably we're not getting. So let's scrap the AI code for a moment. We start with count. First off, easy bit. If let sum children is self.children, then we're going to do count plus equals children then, as I said. This is why it should have been a U size. Now what's this going to do? We're going to start with com. Com has 1 child, we're going to go to 1. And then we stop because we're not iterating over anything. So then, for child in children, does count children need a level indicator? Is that the easiest way? If we say that this is level 0, i.e. that's a direct orbit, then we add on, we do 0 plus the number of children it has. Then we recurse and we say we're level 1, and we do 1 plus the number of children it has. So B, we add on 1 for every child it has, 1 plus 1 for every child it has. I.e. this child is worth 2 and this child is worth 2. These children are worth more, they are better. And then once we get to D, we're at level 3. Yeah, that's it. That's, I think, going to be it. Level is going to be a nice size. This should all be U sizes, but it's easy to do it here. So it's going to be for each child, count plus equals level, count plus equals count children, child.count children. Child.count children, level plus 1. What don't you like? Oh, I'm not iterating. Right, yeah. For child in children. New. That's not what I wanted. I wanted that. And you're unhappy. And we start at level 0. How do we do? We got closer now, we're at 31. So let's do this test for a moment on simple. Just quickly. Because I think that's going to be easier. It's definitely not supposed to be 4 to 2, but it's now giving 4, which is definitely wrong. But it's much easier to reason about. So, let's break there. And we'll debug on tests. Okay, we are at com. Level is 0. Excellent. We do indeed have children. It has size 1. So for each child, do I need to start with level as 1? Is that the problem? Because we should have added 1 there. I think that might be the problem. Easily fixed. I can't remember what I said this should come out as. Obviously, we're still testing 8. Is 8 right? So, there's one direct orbit there. That's a 2 and that's a 2. So that's 5 in total and that's a 3. So 8. Yes, perfect. Great. Let's do that on the original. Should be 42. And it's passed. Sweet. Right. Well. Right, we're not actually calling part 1 on, what did I call it? Head. Why are you test data? You shouldn't be test data. You shouldn't be data at all. You should be head. And it needs to be a reference to head. Ooh. Interesting. Owning node not found. Shit. Shittity shit. So, this comes from our from string, and I said, hopefully we'll never get in here, because our data will be ordered. And I won't ever need to think about creating a node that orbits a body that has not yet been created. Hopefully. Possible there's a bug. We can replicate this by doing a bit of reordering in our test. So if I put K up here and run cargo test, yeah, I know I can up tap twice. We'll get owning node not found for L, right? Because K is on line 9, doesn't get created until line 11. What is the easiest way to deal with this? The easiest way to deal with this is to have a vec of floating nodes. Oh, I don't like this at all. Right. Mute orphan nodes is a vec. I could have just had an empty one. So if we get here, we are going to push into orphan nodes. When we are searching for that one, we also need to search every node in our orphan nodes vec. This is probably the fastest way of, well, it's not the fastest way of doing it, but it's the easiest way of doing it, I think. So not only do we need to search through the entire vec, but for every item in the vec, we then need to search for getChild nodes. Okay. So the first thing to do is search orphan nodes. So search existing orphan nodes. If not found, create a new orphan node. And then at the end, before we return head, I'm going to put this here, just so that we don't get past this point. Haven't inserted. To do is probably a much better thing here than panic, actually. To do, insert orphan nodes into the tree. Right, okay, so let's do this straight up. Don't think I need a ref mute. I do need a. I do not need a ref mute orphan nodes. Just need a ref. Think. Ooh, maybe I do need a ref mute. Yeah, I do. Okay. Did getChild node? Does it search itself? Get child node. If self.id is self-return, yeah, okay, perfect. So I don't need to do that. I can just go straight to node.get child node ID. Ref ID. If let sum n is some parent is that, then parent.insert child and break will take us out of our for loop. We need to know if it was inserted, because if it wasn't inserted, we need to push it into orphan nodes. So orphan nodes can themselves be parents, that's fine, and then we'll sort of try and align the whole thing at the end is the idea. Oh no! No. Maybe. Yes? Go grab Day 6 test again, which is just publicly on the website, so I don't think it's a problem to share. So if we do, let's just put them here for a moment. K will have L. This isn't the best example. I think I want J to move. Yeah, so J is going to go up here. J does not have a home. J does not exist, so K cannot have a home. That's what's happening. So we're trying to create a child K and give it to parent J. J does not exist. So we are going to create an orphan node K, which has an ID of K and no children. It's going to go into orphan nodes. Carry on. That one works fine. This one works fine. This is where we need to insert it. Which means I need to keep track of the parent that is missing here. This is going to need more than half an hour of stream, and I should probably pause and think about this. I suspect there's a very obvious solution to this that I'm missing. And this is starting to look much more like just doing straight up linked lists and being able to insert in the middle of them. You'd still have orphan nodes. It's a double-ended linked list, right? You need to know who your parent is. That's the problem. Ooh, this is only useful in this one situation. I'm going to have to do it, aren't I? So, right, an orbit node has an ID, it has a parent ID, which is a string. Parent ID is ID to owned. It is a sum, it's an option. Option string. Just because otherwise I need to do empty string and I can't be bothered with empty string. Parent ID is none. That's fine, that's fine. What don't you like? Yeah, you're an OK, you're a sum. Sum. ID to owned. This isn't actually important. I'm never really going to check for a parent ID. So I probably could have got away with the empty string, but it's kind of more rusty, I guess. That bit goes there. And you are unhappy because you need type annotation. Right, okay, yeah. So this will sort itself later, but for now, I'll just make that happy. I'll do that in a second. Tests are going to be wrong. Yeah. Ooh, I don't like this at all. Right, I need my day 6 simple. I'm going to fix the test, and I'm going to check the test work before I go and do the ordering thing, because I know that this should work anyway. So the first one, I, has a parent node, a parent ID of some D to a string. This is disgusting. This conveniently gets around the fact that it's not going to own. It's not going to have a reference or own its parent, but it just does mean that we're going to need to do a lot of searching. Some soul searching, perhaps. D is owned by B. C is also owned by B. B is owned by com. And com is none. So let's get rid of you. Let's get rid of all of you for a moment. We'll have our panic back. And our test pass again. Great. So now what we are going to look for is swapping those around. Yeah, D doesn't exist. It would have been much more sense if I did it on day 6 simple, actually. Cool. So if I run this now, this test will fail. And it will fail because it panicked, saying... well, I didn't panic saying anything because I didn't put anything in the panic. But let's take these out. So, we are in a situation, we are here. We've created D, but D doesn't have... We're trying to put E in D, D does not exist. That's the problem. Oh! Oh, I don't need parent node, parent ID at all. I just need to create D, put D inside the orphan nodes, give D E, and then when I get to this line and say B owns D, check orphan nodes for something with the ID of D, and then if not, create it and then put it in. Right, yep. You don't need to know that, that's much better. You can go, you go. So, create parent and insert child, push parent into orphan node. That's all that needs to happen here. Okay, it's that when we get a new line, which happens here, check if child exists. Yeah, check if child exists in orphan nodes. And push. If not, create and push. Cool. That's it. Right, and now I need to go and undo all of my test damage again. Yes, this feels much better. Right. Stick you over there. So, right. We have come across a situation where we've got a D and E. We have not found a node with the ID of D. So, let me... Well, we'll do the child first. Let child be an orbit node where ID is child ID. Child ID, which is a string, and it's going to own it. Children is none. There was a much faster way of doing it. Let parent be an orbit node where the ID is ID just called ID. Yes, it is. So ID is now not going to be usable after this. and we give that some vec child. What don't you like? Use of mood value child ID. Where was it used? Oh, we've already created a child. Goodness me, that was 25 minutes already. We've already created child. So child, we didn't do it anymore. And then orphan nodes, bush parent. Great. Mute part, ID, child ID. Create child. Is that still what I want to do? Or orphan in orphan nodes. If let sum found is orphan.getChild node child ID. I'm going to be explicit. You can label loops in Rust. And this is just because I don't want to have to think about where I'm going to break here. If let sum found equals head, not head, is orphan.getChild node ref ID. Found.insert child and break inner. So break inner is going to break this loop. No, this isn't right, is it? Because effectively what I'm going to have is I'm going to have orphan node. Vec will have one orbit node, which is D, which has a child of E, and it's just floating there. Then we say, okay, ID is B and the child is D. If somewhere in my orbit nodes I have an orphan, I think I just want the straight up ID, right? Is it possible that I could end up in... Yeah, because something could be added onto E. So, okay, I want to get a node with the label of the child ID. Yeah. So I need the child ID. Oh, fine. So this is basically, we move the child ID because it's now owned by orbit node. By the child, the orbit node we've called child. And only one thing can own a piece of data at a time. I'm trying to take a reference to it, but it's already been taken here. Actually, I don't need to do this. All I need to do is do ref child.id. There we go, that's better. So now we're going to search, in this case, we're going to search for a node called D, and we want to insert D into our node B. Does B already exist? Well, I mean, it does. Can we guarantee B already exists? This is wrong. So what's going to happen? Because if I get E, F, so there's going to be a node called D in orphan nodes, which has a child of E, which has no children. Then we're going to say, well, actually, we need to go find E and give it F. So that's one case. And that's going to be that we are looking So in this line, we are looking for the parent, E, and we want to insert it into F. I think this needs to come after the normal case. Okay, this stream is getting too long, so let's get rid of this and just write down what needs to happen. So this bit is fine. Create a parent node and insert child. So long as... So we're going to start out by searching main tree for child. Otherwise, search orphan nodes for child and insert. Then we are going to... Nope, that's fine. That's fine, and then at the end, we need to insert all the orphan nodes into the tree. That's it. Okay. Whew! Maybe I should just kill this tree. No, fuck it. Stream of consciousness. This is what you get.